So we're going to continue having a look at this. So this is where we left off, the fully unoptimized, very inefficient demo. So you can see here, my draw's taking a very long time. My update's fairly stable at 109 microseconds, but my drawing is taking 900 to 1,000 microseconds each frame, and that's basically because I'm uploading data each frame, and I've deliberately not made it very efficient. So in our next demo, which is the CPU, and I've also restructured things to a structure of arrays, which I'll talk through. If I run this now, you can see that, well, firstly, my drawing is negligible now, it's sort of 7 or 8 microseconds. So I've overcome the naive and almost immediate mode approach of OpenGL. And again, if I just run both of them side by side, what we should be able to see is that I'm also getting an incredibly stable update time, but you will notice that the update time is actually quicker on the unoptimized than it is on this version here, which is something that is worth having a look at. But so whilst this is quicker, I have got a slower update time, but all will become apparent when we have a look. In overall terms, this is faster because drawing is taking a lot less than this one here. So we'll begin to look at these sorts of things. The other thing that we can also look at is if we up the number of particles now, so we're running about 10,000 in the simulation there now. You can see my update is sort of 20,000 microseconds there. If I just do the same to there, my update is less, but look at the draw time, far quicker, slower draw time. So the overall simulation time now is still much quicker in this demo than it is in this demo, and you can really sort of begin to see that in the sort of the things that are going on. So let's have a quick look at this code. So the first thing that I've done in this code is I've got rid of the particle.h structure that I had previously, and what I'm doing instead now is I'm creating internally to my grid class now a stood vector of positions, a stood vector of directions, a stood vector of accelerations, and a stood vector of max speed. So basically what I'm doing here is I'm ensuring that my data is now basically in a structure of arrays format. So each thing has its own array. As we'll see later, formulating data in this way makes our life a lot easier when we begin to look at how we can do things in parallel, which is what we're going to build onto. So slightly different reordering and restructuring of what's going on here. So first thing is we are setting the number of particles here. We are then resizing all of our arrays to be the size of the number of particles. Again, this does now mean that we've got a slightly longer update of resizing them all, but and there's a bigger memory footprint perhaps, but that's initializing all that. And Init Grid is now going through, instead of as we did it previously, we loop through for the number of particles, passing in our subscript I, and then we set the individual parameters for subscript I in there. And you can see I'm actually setting the X, the Y, and the Z components of the position individually. And I'm zeroing out the Y's here because we're doing a 2D simulation, but I'm still storing my data in 3D. And the other big difference now is I'm creating a vertex array buffer now, and it's using the multi-buffer VAO. And I'm creating a buffer for my vertex attributes, so my position and my direction. So there's two buffers now. I'm going to upload the first buffer is going to have the point data, the second buffer is going to have the direction data. Input 0 of the shader is going to be positions, input 1 is going to be the directions as previously. And you'll also see here that I've got a raw OpenGL buffer that I can generate as well. So I'm doing basically two different versions. I'm using my NGL and a raw one, which does exactly the same thing. Same speed, it makes no real difference, but I can toggle the draw modes between the different ones to either go to a multi-buffer one or a single OpenGL sub-buffer mode, and I can swap between the two of them by pressing a key. So in NGL Scene you can see here that I can just toggle the different draw modes by pressing either key 1 or key 2 for single buffer or double buffer. So if I just run this, well, you can see that the data, so it defaults to single buffer. If I flip, you can see there's very little difference between the two that are going on through there. So there's negligible using my NGL library versus raw OpenGL, but it's worth just testing this sometimes to see whether that could be a bottleneck. And in fact, what the bottleneck is going to be, so here's our update. The update is exactly the same as we did previously. The only difference now is obviously that we're working on individual components, so our dir arrays are going through for each of the particles in there, doing the update like that, checking and doing the reflectors before, and that data is going through. And then when I draw, if I'm using my multi-buffer VAO, what I'm doing is I'm making a call to map buffer. And what map buffer does is it makes a call to GL map buffer, and it returns a pointer to the data that's stored within the OpenGL context, so effectively the data that's part of the graphics state, into our client program, into our program. So we've basically got a pointer to that data that we copied previously, and then what I'm doing is I'm making a call to memcopy to copy that data through. And this is going to be where most of our bottleneck is, these two memcopies here. You can see also what I can do is I can just make a call to GL buffer subdata, which does effectively the same thing. So in this raw version, I'm just making a call to GL buffer subdata and recopying that data across each time. Either way, this is going to be where our particular bottleneck is going to be in our code. And again, if we just do a quick setup, so I'm going to set my breakpoint there, and at the end of the program, if we start this in debug mode, it should fire up our diagnostic tools and profilers. Got record our CPU profile there, so I'm going to continue, record a few frames of code so that we've got something to measure. So you can see everything's running nicely here. One thing to notice here, you can see CPU of all processors there, so we're not really maxing out our CPU in particular or anything else within running all of this. So if I stop this now, we should grab our diagnostics, have a quick look and see where things are occurring, and we can start to if we just open details. This gives me so function body, called functions. Oops, not giving me much information there. I don't know why. Let's go back through, having a look and see where our hot path events, memory, CPU usage. It's not really giving me much useful information there. Accessing, well, that is causing some issues, which is a subscript operator of std vector. Let's go up and look at what our hot paths are again. So if we look through here, there's sort of some of the Windows DLL stuff and things like that, core application, so the Qt event loop, which is obviously, as we dig down, we can begin to see, and it's this one. So I would say the biggest part of what's doing things is the NGL set data here. So it's us copying the data to OpenGL is causing us some of the biggest issues there. So the first thing that we want to really begin to look at to optimizing is better and more efficient ways of passing this data to OpenGL, and we're going to sort of delve into that in the next video. I think most of the other bits and pieces, if we sort of delve through here, if we have a look at update in here, so text rendering is a bit slow still. our update isn't appearing to do. Where is my update? Find update. Grid update. It's 6% of the overall sort of time, so it's not doing much at the moment. But if we look at grid draw, 0%. Why is that not giving me too much? Look, reach the end of the document. Yes, there we go. So PaintGL, we can see, is a pretty hot path through all of our code here, and if we were to delve through to this, we should be able to sort of see all of this code is. There we go. So rendering text is actually prohibitively expensive, which is not surprising really. It's very inefficient rendering text, and one of the other things that may be causing some issues is the draw there, which again is hard to tell at the moment. So first thing I need to do is to try and figure out a better way of drawing quicker. And there are many ways to speed things up with OpenGL and to get drawing quicker. The approach that I'm going to take here is I'm going to try and pass less data to OpenGL, and in particular what I'm going to use is an idea called a texture buffer object. And I'm going to formulate all of my data into a texture buffer object and send that up each frame to make things a bit quicker. So the next video we'll have a look at the structure of the code for that. But to bear in mind that the most important thing at the moment is we've converted our code from being an array of structures to a structure of arrays.